Okay, so here we go, real quick. Let's see. Which group wants to help us out here? What's our strategy on this? Volunteers, strategy. What are we going to do? Colton, what do you guys think? What's our strategy finding horizontal tangents? Okay, good. So, good. So, horizontal tangents, that means horizontal lines have slopes of 0, right? And so our strategy is going to be, we want to know where is the slope of the function, aka slope of the tangent lines, equal to 0, and that's the job of the derivative, right? In calculus, we associate the derivative with slope. That's its job, right? And so now in differentiating this, this looks like a big function, but this is a really easy one. Polynomials like this are our friends. They are the easiest functions to deal with in calculus. How do I differentiate a string of polynomial terms like that? Yeah, okay, good. So I'm just going to use my power rule, but I'm just going to break them up. We will call this, and our language for this in calculus, and I want you to kind of gradually get familiar with this. This is what we call differentiating term by term. I think I've mentioned that before. That just means we can break this up into a bunch of really simple derivatives. Each term represents a simple derivative, right? And so all we got to do then, what's the first term when we differentiate? Okay. And then the derivative of constant? Zero. Okay. So there's our derivative. All we're going to do is just set that equal to 0, and we end up with a quadratic equation. So when we solve that quadratic equation, what are the solutions going to be for us then? If I were to solve that, and I've got a bunch of ways I could solve that. If I'm using technology, I could graph it, or I could use the polynomial solver. If I'm not using technology, I got quadratic formula. You know, maybe it factors, but honestly, if this first number is a 3, yes, I don't know if I'd even try to factor it. I mean, you can, if you want to spend the time, but I would probably just throw that in the quadratic formula if I don't have access to a graphic calculator. Yes. Okay, so what are these? We get answers for x. X equals this or that. If my answer, what do I do with those solutions? What are they significant? Remind us again in the context of the problem. Yeah, those are going to be the places where the slope is 0, right? Okay. Those are the values of x where we have horizontal tangents then. Okay. All right. So does that make sense?
Yes.
Okay. Let's skip this one in favor of this one. Okay. Now, who would like to get us started on this? If I want to find the derivative of this big, ugly function, that is pretty complicated looking. Now, as we look ahead a little bit in calculus, we're eventually going to learn techniques for taking derivatives of quotients of big functions and products of big functions, and you know that's not very far away. But for now, we don't have that stuff. For now, we have a very limited bag of tools for doing derivatives. We have a couple of trig, sines and cosines, and the power rule, and that's it. So in order for us to be able to take a derivative, we have to be able to drill this down to just a sum of terms, to which we can either apply the power rule or our trig functions, but obviously there are no trig functions here. So this is all power rule stuff, right? Okay, so take a second with your group and look at how this is gonna work. Not getting recorded. So bad. Okay, next one. Yeah, if I take the 3 down, 3 times 2 9ths is 6 9ths, which reduces to 2/3. X squared. Next one. Next one. Okay, so there's the first derivative, the first order derivative, okay? What's the second derivative? I put 2 hashes there. We'll talk more about the notation, maybe next section, but for now, that's good enough. The second derivative just means the derivative of the first derivative. So what am I going to get for that? Everybody seen where we're getting this? Bring the 2 down times 2/3. Okay, well, let's keep going. We could do the third derivative. Okay, and then now you can see here that this is going to start to get tiresome putting all these hashes up. It's going to be hard to count. So here's what we do. Eventually, we just do this. If I put it in parentheses like that, it means that's how many, that's the order of the derivative. And then finally, zero. So finally it disappears. Yeah. Okay, make sense? Okay, so that's all we mean when we talk about the orders of a function. It's just the successive layers of derivatives. That's it. Okay. Oh, you know what? That's a bad. Okay, this is a graphing calculator one. You know what? This problem I shouldn't have assigned this. Should not have assigned this. Can we do this one? Do we anything we set our minds to? There you go. Okay, let's try something. Let's try doing this one using technology because we don't yet have the.
What is technology?
Technology, yeah.
Oh, you mean them electron thingies?
Electron. Okay, and we have to do this one, and once again, we can't do this problem any other way right now. Until we know the quotient rule for derivatives, we can't do this, we can't take a derivative of this, and that's a little ways away. We got a couple weeks before we get to that. So we've got to do this one graphically. So I get 6x divided by the quantity x squared plus 1. Oops. Okay, and I'm just going to go zoom 6 so I get the same window. Okay. And if I want to find, let's do how about if we just do the one at the origin? Well, maybe we'll do that. If we have time, we'll do one more, but at the origin. So first of all, do I know that this graph actually goes through the origin? Well, to find out, I could just, how do I know the y value if I input an x value? How do I ask my graph to do that for me? Say it again. Calculate, okay, so second, calc, value, and then type in x equals 0, and it tells me the ordered pair. So at that point, y equals 0, right? There is a shortcut for that. Anybody know the shortcut? If I've only got one function graphed, if I have multiple functions graphed, this doesn't work. If I have one function graphed, I can just go trace button, enter the x value, and it takes me right to that step. So trace, 0, enter, gets me that a little quicker. Okay? So I know then, let's keep track of this stuff. So I know that the coordinates at this point right there are 0, 0, right? All I need then is the slope, and then I have a pretty simple algebra problem to do. If I know the point and I know the slope, you guys can take it from there. To find the slopes, anybody know how to do that on the calculator? I will show you. Yeah, it is second calc, so we go second calc. And this probably never made sense in the past, but now it does. Look at the 6th option. Dy dx, how about that? So if I hit 6, and then I'm gonna enter an x value. If I put in 0, it tells me the slope at that point. Okay? Now, how about that? Ooh, tricky, huh? Didn't know your calculators would do that. So now what is this? There's always going to be, being as the TI-84 is using some, it's kind of fighting a constant war internally. It's trying to pick algorithms that its puny little processors can handle doing repeatedly and quickly, but sometimes some error gets built into those. So what is this thing probably trying to tell us? 6, yeah. Okay, so, and certainly if we round it, it's 6. But this is really trying to say 6. So then we know that the slope at this point so that's pretty simple now, right? I've got a point, I've got a slope, you know, algebraic manipulation, and we got an answer for a line, right? There it is. Let's do maybe the one at x equals 1. Now, they told us the y value was 3, but we didn't even need to know that, did we? Because we could have just gone trace 1, enter, and it tells me it's 3, right? So we've got then this point is at 1, 3, and if I want to calculate the slope there, just second calc 6, x equals 1, and it's telling me dy dx is 1.5 e negative 6. What's that saying? 0. Sure. Okay, so that's, in other words, that's 0.00000015. So that's the calculator's numerical way of trying to get at, but not quite getting it perfect. 0. So we could do this problem technologically. Okay? Make sense? All right. Okay, moving on to the stuff I want to get to. Yeah, here we go. Finally, we get some physics. Simple harmonic motion. That just means springy motion. Motion that's following some sinusoidal curve, which is repeating itself back and forth like this. Okay. So here's our position function this time. Let me make this a little bigger so you can see it. So we have position as a function of time equals 9 minus 5 sine t. Okay. Let's maybe graph that and see what it looks like. Okay, so if we how about if we go into let's put ourselves in radian mode. So mode, make sure you're in radian mode. If you go mode and then it's you want to be everything should be if you want to get into like physics mode, everything should be on the left. Everything highlighted on the left. So you're in radian mode, etc., etc. Real, not imaginary, etc. Okay, so now if we go to y equals, we'll just put in this function. 9 minus 5 sine. We're going to call it t on our calculator? X. Okay, and then we'll go zoom, zoom trig or zoom, something like that. We go zoom trig, number 7, zoom trig. And if we go zoom trig, oh yeah, because it got pushed up so much, yeah. So we'll go zoom 6. You're right, zoom trig didn't work well. Okay, so in fact, even zoom 6 didn't work great because it went up to 10. What should it probably go to? If it's going to be 9 minus 5 sine t, let's just think about this analytically for just a second. Between what values is sine t going to oscillate? What are the output values going to vary between? I know that's bad grammar, but bear with me. Sine t, the smallest output value of sine t is what? No. What's the sine function here? Sine and cosine both oscillate between maximum value of 1 and a minimum value of negative 1. Okay, so the sine is going to be outputting that range of values, right? If I multiply that by negative 5, that's going to change that to what? Up 5, down 5? And then 9, if I'm starting at a baseline value of 9, that's my vertical offset. So I'm going to start at 9 and go up 5 and down 5. So between 14 and 4. Okay. So what if I made my window go from like I don't know, how about 0 up to 20?
You're an X right now.
Oh, you're right. I am. Just see if you're paying attention. Negative 10. So 0 to 20 will certainly capture that. And how about if we go, instead of going from negative 10 to 10 on the X, let's just go from negative 2 pi to positive 2 pi. And look how we do this. I can actually put in negative 2 times, this is kind of slick, times pi. When I go down, look what it does. Oh, it makes a decimal for me. Okay, to positive 2 times.
You don't have to do the times sign.
Oh, yeah, you're right. I probably don't. Okay, good. So there's my position function, right? Okay, now remind me real quick here. Velocity, how is velocity related to position in terms of the calculus? Good, okay, velocity is the derivative of position, right? So if I want to know the velocity function, this is pretty simple. Whoops. V of t is going to equal what if I differentiate this term by term? Derivative of 9 is 0. Okay, now I've got this negative 5. What's the derivative of sine? You remember? Cosine. Good. So I've got my derivative of sine is cosine. I've got my negative 5 out front, right? So I'll just leave that there. So there it is, right? There's my velocity function. Now let's just graph that alongside the position function for a second and just see if that makes sense. Okay? Any questions on that so far? Okay, and this is just going back to, you may have forgotten that, but that's one of the standard forms, one of the tricks that we talked about the other day. Okay. So let's graph that. If I go down to y2, negative 5 cosine x. Oh, I did. You're right. Negative 5 cosine. So now if I hit graph, way down at the bottom, I got to probably go back and change my window again. I'm going to go down to, instead of starting at y min is 0, I'll go to negative 5. Okay, let's see if this makes sense. Okay, does, oops. Okay, does this make sense? Can I make this bigger? I think I can. I want to. Oh, I can't figure it out. Anyway, that's big enough. So look at this thing here now. Okay, does this make sense? If we look at my, and I'll make it blue, here's my original function. Right, there's S. And the red function is the derivative. See if you can see this connection. At least a couple key points on this. Remember, the red function is the derivative function, so the value of the derivative function, the y value of the derivative function equals the slope of the function, right? So does it make sense? Let's look specifically at the zeros. Did these points make sense right there, and there, and there, and there? Okay.
Tomorrow.
Tomorrow. We'll keep going.